Good morning, fourth grade. So for the past couple of weeks, we have been learning how volcanoes form. We have seen that they form underground when the plates are pushed against each other and different pressure from the material underground called magma pushes up creates. We have also seen how magma erupts from volcanoes. And when magma erupts from a volcano, it is called lava. After lava erupts from a volcano and it hardens on the ground, it becomes hard rock and it becomes a part of our earth. Yesterday, we investigated a specific mountain called Mount St. Helens. We used our topographic maps in our science packet. This topographic map, and we got to create a profile of what Mount St. Helens looked like before it erupted in 1980. Then we compared it to our second map that we see here. This is the new topographic map, which shows the shape of Mount St. Helens after its eruption in 1980. Using both of those topographic maps, we created a profile that looks like this. Using the topographic maps, we were able to create a profile for Mount St. Helens. We created what Mount St. Helens looked like before its eruption, and we got to follow it. It started at its elevation of 1,600 and it went all the way up to its peak of 2,900. After Mount St. Helens erupted in 1980, it got smaller and its peak was at 2,400. Today we're going to watch a video to learn more what happened on Mount St. Helens that caused the mountain to get smaller. I want you to get your profile map, and we're going to add some color to it so we know what Mount St. Helens looked like. If you don't have your profile map, that is okay. Just continue to watch along. Here is the profile of Mount St. Helens. I want you to get either a marker or a colored pencil of two different colors. I am going to use the color red to trace this line that shows Mount St. Helens before its eruption in 1980. So take your first pencil, your first either colored pencil or marker. It can be the color red or any color you have, and trace the first line. The line that we traced with the color red is the profile of what Mount St. Helens looked like before it erupted in 1980. We're going to right at the top with your red. I want you to just draw like a little, draw a couple of lines. We're gonna make a key. And next to it, we're gonna write Mount. We're gonna write the abbreviation for Mount, which is MT. Helens. Before 1980. So this is our key, and this key tells us that this red line is what Mount St. Helens looked like before its eruption in 1980. Its elevation before its eruption in 1980 was at 2,900. Now I want you to use a different color marker or color pencil. And we are going to trace the line of Mount St. Helens after its eruption in 1980. Now, what was interesting about Mount St. Helens after its eruption in 1980, that the profile or the way the mountain was set up on this side, the letter A, that is the south side, it stayed completely the same. It wasn't until we got to this side, the north side, that the profile of Mount St. Helens switched. So I want you to take a different color marker, I'm using the color purple, and trace the outline of Mount St. Helens. And we're going to write a key at the top. Just draw a purple line. Mount Helen after. Ooh, sorry. The purple line shows us what Mount St. Helens looked like after its eruption in 1980. Usually when volcanoes erupt and they spew out lava, the lava hardens on the land and it becomes rock, and it usually adds to the volcano, making it taller. However, the eruption for Mount St. Helens was different. We are now going to watch a clip of scientists who were exploring Mount St. Helens during 1980 to explain what happened.
The eruption of Mount St. Helens on May 18, 1980, was one of the most dramatic geologic moments in American history. For 2 months prior to that eruption, scientists with the U.S. Geological Survey and the University of Washington's Pacific Northwest Seismographic Network had been closely monitoring the volcano.
All the deformation on the mountain was local to the mountain, and even more local than that was on the north side of the mountain only. In the nearly 2-month period before May 18, what was essentially happening at Mount St. Helens was that magma or molten material was moving up from some deep reservoir beneath the mountain up into the volcano itself. And it began to grow or form what we call a dome or a cryptodome inside the volcano. And that inflating body of magma or molten material actually broke the north side of the volcano and began to cause the north side of the volcano to expand out toward the north.
We were measuring the rate of northward movement of the bulge at about 6 feet a day, and we knew that wasn't so good.
On the morning of May 18, I was driving up Interstate 5, headed up to the north side of Mount St. Helens with some parts and some batteries for our time-lapse cameras. And as I glanced over at Mount St. Helens, it was a beautiful blue sky day, and the mountain was sitting out there, and suddenly I saw this mushroom cloud go up above the volcano and climb rapidly up into the stratosphere. I was down in the room where the seismographs were at 8:32 in the morning, and I heard a sound, and I just looked over my shoulder, probably just a split second after the earthquake, the big earthquake had started, and saw that this was something very large, larger than we'd seen before. Watched it for a few seconds just to confirm that. And we were off the ground probably at 9:05 or something like that. I mean, it was really, really rapid, and got up to the point where we could really see the mountain well. I suppose between 9:20 and 9:25, something like that. There was this terrific, very vigorous vertical eruption column. There was the stem of the mushroom or the toadstool that then blossomed out at greater height. And for most of the morning, we saw this tremendous ash cloud roiling out toward the northwest, and I can only assume that was coming off of the big pyroclastic flows that were going off in that direction that later built the pumice plain. It was a very eventful morning. On the morning of May 18, what actually happened? The landslide basically uncorked this pressurized body of magma and allowed it to explode or expand out towards the north very rapidly. This is what we call the lateral blast. It was a horizontally directed explosion of incredible magnitude. It caused this expanding cloud of ash, rocks, and gases to move out across the countryside to the north at speeds of several hundred miles an hour. The directed blast was really the most destructive event that occurred on the morning of May 18. It completely destroyed an area of 230 square miles in a matter of somewhere between 5 and 9 minutes. It essentially killed every living thing within an area of 230 square miles, and it destroyed hundreds of acres of virgin forest.
The eruption of Mount St. Helens on the morning of 1980 happened right after an earthquake. The earthquake had caused a lot of the rock plates that are underground to shake. The shaking of those plates caused the rock material that made Mount St. Helens to begin to break off. The shaking caused breaking of the rocks, and it caused a landslide, causing the rocks that were on Mount St. Helens, especially on the right side, to start to fall off. Also, the magma that was there was also shaking, and it continued to bulge and get bigger and bigger. When that earthquake hit and the rocks broke off, creating a landslide, that is what caused the eruption of the volcano. If we notice, the left side of the volcano stays pretty much the same. That is because the landslide only occurred on the right side, and when that landslide fell all the rocks, the lava erupted, completely taking out everything on the right side.